With atomic orbitals, what we want to be able to remember from general chemistry is that quantum mechanics was established as a theory to explain the wave properties of electrons. If you remember Schrodinger's cat, which we'll tell the story in class, Schrodinger's cat was a thought experiment to identify the idea of wave-particle duality. And so the wave function is a plot of the probability of where we could find an electron in the electron cloud. We can remember on an XYZ plane, we think here, Y, X, and Z, however you like to remember your XYZ 3D Cartesian planes. The S orbital was a sphere, and the P orbital was a dumbbell shape, or the figure 8. And these were all probabilities, one side shaded one color, the other side shaded with the other color. All of these were probabilities of where we could find the electron in a given electron cloud. And so it's really with these shapes that we're understanding the idea of electron density, right? Again, it's a probability. It's not an exact location, but what we want to be able to think about is these are where the electron density could reside, the actual volume, the space occupied by an electron itself. Now we see that there are sometimes shades specifically for those p orbitals. The electron can behave both as particles and waves. So this idea that it can have wave-like nature where there's these hills and valleys, right? And so there's positive and negative really nodes separating these positive and negative areas of the probability. And so you'll see specifically the p orbital is shaded red and blue in textbooks. You might see for our purposes and for our drawings that we just shade one side and we leave the other side white. You could do it the other way where you shade the bottom. We just don't ever want to see, this is a big old N-O, no, don't do this, the whole thing shaded, right? It's not all one color. Don't do that. It's not all blank either, right? Yes, this is the shape of a p orbital, but you got to shade it somehow. So be very, very careful with that. We are trying to understand the full in-depth craziness of quantum mechanics in a simplified way. It doesn't mean that there's a positive charge or a negative charge depending on where the shading is. It's just looking at the sign of the wave function. And so we'll take that simplistically. Now, electrons are most stable in lowest energy orbitals. So we start with the 1s, and then we went to the 2s, and with the n equals 2, we got the 2p x, the 2py, and the 2pz. We got degenerate orbitals. We can think about our electron configurations. We'll see the orbital diagrams in just a minute. I just want us to focus on the difference between 1s and 2s. Notice the 1s is smaller. As n increases, the size of the orbital increases. We will focus mainly on s's and p's. Since we are dealing mainly with the first and second row of the periodic table, we don't do a lot of d's. Even going into things like expanded octets, we usually don't even talk about hybridization past sp3. We don't talk about the 5 or 6 domain molecules. We usually stick with tetrahedral or trigonal planar. Things hopefully are starting to have us remember these terminologies. But looking at our 1s orbital compared to our 2s here, size is the big difference. And then with the 2p's, it depends on whether it's on the x, the y, or the z axis, right? That's how we define those degenerate orbitals. And if we remember the word degenerate, they were all equal in energy. Doesn't make a difference. The y, the x, or the z are all the same energies. And so when we started to draw the electron configurations from the orbital diagrams, we used just the build-up model, right? The off-bow principle. And when we got to the two P's, we used Hund's rule. You put one in each before you pair. Pauli exclusion principle, we can only have two electrons in a specific orientation at one time, as long as they were opposite spins. All of those about our electron configurations still hold true. They are very, very important for us. So hopefully you still remember them from general chemistry, and we can move on. Now with valence bond theory, it's talking about how do those atomic orbitals, S's, P's, T's, how do they overlap? What do they do when they do a Venn diagram to bring the shared internuclear distance together? What is happening? Now, if we remember a little bit about constructive and destructive interference, if we are bringing waves closer together that are constructive, they form one big space. This is good. This was bonding. If for some reason we bring opposite phases together, this is what we call canceling out or destructive, when a node appears in the middle and we start to see insufficient bonding. The bonds for an H2 molecule, hydrogen diatomic, result from a constructive interference. So if we can think about the 1s orbital with one electron and the other 1s orbital coming together with the other electron, what we tend to start to see is just a big ol' cloud or a Venn diagram of bringing them together. Direct overlap was the key word. And that is what we called a sigma bond. We abbreviated it with sigma as well. Now, when the orbitals directly overlap each other, head-on overlap, that is the strongest type of bond. We'll talk about parallel overlap in just a little bit, the pi bond, once we get there. Now, in molecular orbital theory, this is where we started talking about bonding and anti-bonding orbitals. We might not have gotten too far in depth with them for general chemistry, so let's just see what happens. If we take two atomic orbitals, these guys, I'm going to abbreviate those AOs, atomic orbitals. If you put two things together, you're going to get two things out. Bonding is always favorable, lower in energy. This is what we call a sigma bond or a bonding MO. But when I put two things together, I always get something that is destructive as well. I get the constructive, which is bonding, and I get the destructive, which we'll call the sigma star, little asterisk up there. Sigma star is how we phrase it, or we call it the anti-bonding. We won't spend too much time discussing anti-bonding MOs, but we will see them a little bit in chapter 4. Singular MO right there. Now, when we think about looking at that MO diagram right in the middle, right, I'll highlight them blue right here. These are molecular orbitals, the sigma and the sigma star, the bonding and the anti-bonding. When I look at those and I take the two electrons that I had, one from either side, one from either hydrogen, I would put them in the lowest energy orbital. That's the off-bow principle, right? That is why H2 exists. There are two electrons in bonding and there are no electrons in the anti-bonding orbital. Now, when we look at this idea, in terms of Venn diagrams, in terms of the constructive versus destructive, looking at the node in that anti-bonding orbital, this is unstable. That was the destructive interference. Over here, bonding, stable. It's the constructive interference. Now, there's a couple other things that we're going to talk about later on that I just want to make sure that we present. The lowest unoccupied molecular orbital, or the LUMO, is this one right up here. This is unoccupied. There's no electrons in it, and it's the lowest unoccupied molecular orbital. The highest occupied molecular orbital is the one right below it, right? This threshold right here in between these two MOs are where we can start talking about excited electrons and relaxed electrons. The HOMO and the LUMO will be important for us when we start to think about ground state electrons. Now, we want the HOMO to be filled, the highest occupied molecular orbitals, and the LUMO, lowest unoccupied molecular orbitals, to be unfilled. We'll do a lot more work with the HOMO and the LUMO next semester. I wanted to present it here so that you knew it has its place in molecular orbital theory. Now, with hybridized molecular orbitals or hybridized atomic orbitals, what we really want to be able to say is that when we think about carbon and its orbital diagram, let's just look at it here. Energy increasing along the Y. We have the 1s, 2s, and the 2p. This we'll do for carbon, since he's our favorite child. Carbon has 6 electrons total, and what we see is this would be his atomic orbital diagram, or we can even think about his electron configuration. This doesn't make sense why carbon would bond with 4 equal bond length types of carbon to hydrogen bonds in methane over here, CH4. Why does it form the 109.5? Why does it form the tetrahedral? Well, what happens with carbon is actually very interesting. We have come to the idea that the atomic orbitals can actually homogenize or hybridize. This was our idea, that where we have our valence electrons, just the valence, right? We'll leave the core, and we'll take those valence and we'll hybridize them. Now, hybridization involves the linear combination of atomic orbitals. The linear combination of atomic orbitals is a really, really complex mathematical operation that helps us understand how these s and p orbitals can homogenize themselves together to form degenerate orbitals. Now, think about cupcakes. Everybody's made cupcakes or seen people make cupcakes. Watch an episode of Cupcake Wars if you need to. Think about it. You take flour, sugar, eggs, milk, maybe some flavors. If you're making funfetti, you throw in some sprinkles, and you mix it all up together. All of those different ingredients get homogenized and baked into equal looking, hopefully, cupcakes that are delicious, all tasting the same. That's hybridization. We want to take S and those 3 P's, mush them together, bake them into a cupcake. And so we take the S and the 3 P's, the X, the Y, and the Z, and we make them into equal energy orbitals that we'll call sp3, because we took an s orbital and 3 P's. Now, what happens to those electrons in the valence for carbon is now they're degenerate. Now they're equal in energy. Now they can all bond the same way. For the carbon atom, only 2 electrons are unpaired, and therefore it really can only share 2 electrons in its ground state electron configuration. Hybridization is the key to understand that there can be 4 equal unpaired electrons to form 4 equal bonds. Without hybridization, we cannot explain why CH4 is a tetrahedral molecule. So it's very important to understand how carbon makes those bonds. Now, carbon must undergo that hybridization to make 4 bonds, to be symmetrical in its geometry, that tetrahedral. And so this is a diagram where we can start to think about those 4 electrons are reorganizing themselves into 4 distinct degenerate orbitals. What results is the sp3 orbital is kind of like an S, and a bunch of P's fell in love, had a baby, and it looks kind of like a dumbbell, but it's an uneven dumbbell shape, right? We see a bloated lobe there on the red side and a smaller lobe on the blue. You can also draw it without carbon involved, right? Don't forget your shaded side, at least one shaded side there. And so looking at this, it's 25% S character. We took 1 S and we took 3 of the P's. Those are the 75% P character. We mushed them all together. And so when carbon bonds with hydrogens to make CH4, we take that 1 S orbital and we take the sp3 orbitals and we merge them together. So we have a carbon that is sp3 hybridized bonded to a hydrogen that is S atomic orbital unhybridized. Normally, it's the central atoms that get hybridized. Outer atoms can hybridize too, but hydrogen can't. Hydrogen just has an S electron. It doesn't need to do that. And so we see that all of those 4 bonds in CH4 are equal. And so they have to spread themselves out. This is valence shell electron pair repulsion theory, Vesper theory. When we think about spreading out those groups evenly so that they don't repel each other, that they're given enough room. And that's where we get that tetrahedral is the 109.5. This is one of the most important shapes that we have in organic chemistry, carbon with 4 groups, tetrahedral. Anything that has those 4 groups will be sp3 hybridized. Remember the 4 electron groups for a central atom. It will always be sp3 hybridized, tetrahedral as its electron geometry. We'll talk about molecular geometry in a little bit. And then 109.5 degrees for the bond angle. Now, it doesn't mean that carbon can't bond other ways. Consider ethene or ethylene, C2H4. Lewis structure looks like this. 3-dimensional structure is that blue shaded planar structure. So when we look at carbon here, again, what we want to be able to think about, I'll just draw carbon's valence electron orbital diagram here. Same one that we had before. This is for carbon, just for its valence now. When we think about carbon here, let's look at one at a time. We have 3 electron groups. So we only need 3 atomic orbitals to make 3 degenerate hybrid orbitals. The 2p stays up there. These become the sp2. We took an S and we took 2 of the p's. We're counting up electron groups. We still can put 1 of each electron in there. The p is very close in energy to the sp2. They're not that much difference. But what we see now is a different hybridization, a different type of bond. With that carbon atom, think about carbon right here in the middle. Let me make him a little bit darker. Carbon atom right here. He's got his 3 sp2 orbitals, the 3 hybrid orbitals. He's got this leftover p with the lobe on the top and the lobe on the bottom. That leftover p, if we remember, this is where we can have a pi bond. Sigma bonds are where we get our hybrid orbitals. And sp2 is very similar to the sp3 in terms of shape, big old difference here is it's going to have a little bit more S character. So think about it being a little bit smaller, a little bit looking more like a sphere. When we look at that ethene molecule, again, we see that there's an orbital overlap right here between the two carbons. Carbon that is sp2 hybridized bonded to another carbon that is sp2 hybridized. And here is that extra p orbital. That would be the pi bond. A carbon p to another carbon p. This is how we dealt with it in general chemistry, hopefully. That the p orbitals overlap to form a pi bond in a parallel relationship. A pi bond is what I like to call icing on the cake. It's not as strong as a sigma. It just adds a little bit of strength for us. So the pi bond is that side-by-side or parallel overlap of the p orbitals. The electron density of the pi bond is spread out above and below, right? It's all of this and all of this. It's like as if it's orbiting around that sigma bond, kind of like a donut. Pi bonds are weaker than sigma bonds, but they do exist in the same general idea. When we think about MO theory, molecular orbital theory, and we said bonding and antibonding, the same thing goes for a sigma or a pi. We like bonding MOs, right? So when we look at this little MO diagram, it's the same as what we had before. Just so you know that the pi interacts the same way as the sigma, just a different kind of overlap. So now ethyne, let's just amp it up one more time, or acetylene is what we call it. Each carbon in ethyne must bond to two other atoms, so only two hybrid orbitals are needed. If we again think about carbon's energy diagram for its valence, when we see that there's only two electron groups here for that carbon on the left, we only need to take two atomic orbitals, hybridize them to make two sp hybrid orbitals, and we'll have the leftover two p orbitals as well. This would tell me two sigma bonds and two pi bonds. So we'll start to see some idea with hybridization and all of those lovely things. Counting up that two atoms can only have one sigma bond. Anything else, double or triple, all those extra bonds would be pi bonds. There's always only one sigma. So that carbon and this carbon are sp hybridized. Excellent. So if we wanted to think about the three bonds, there's always going to be one bond that is sigma. The sigma bond here for the two carbons is an sp to an sp overlap. And there are two pi bonds where it's carbon p to carbon p. The carbon to hydrogen bond is a sigma carbon sp to a hydrogen s. And again, there's two of them. We'll have a lot more practice with these in class. So looking at this three-dimensional shape, we do see the two different pi bonds. One's there on the front and the back side interacting, and one's on the top to the bottom interacting. And they're, again, icing on the cake to what's in the middle, the sigma bond that's actually in the middle, direct overlap. That's how we get the linear shape. All right, so pi bond, because it's a parallel overlap, is weaker. The sigma bond is the direct overlap. It's stronger. Think about holding hands. I like to think about the pi bond as kind of like a high school relationship. You don't really hold hands, you just see each other, you're like, yeah, we're dating, but it's high school, so it's weird and awkward. Once you get in college, you can actually hold hands now, right? You're not afraid to hold hands anymore. Let's just keep it PC. I have a 3-year-old, remember? So the sigma bond is that direct overlap, holding hands. You are stronger, you are well established. It will always be stronger than the pi bond, which is the parallel or side-by-side overlap, not directly touching each other. Now, when we think about which one should be longer, the sp3 sigma bond or the sp sigma bond, the more S character, the shorter the actual orbital is itself. And so the sp3 is a longer bond, sp3 to sp3, because that orbital is actually longer, less S character, less like a sphere. The sp to sp sigma bond, that sp orbital is actually smaller. It's more S character, so it looks more like a sphere. And so it will hold the other atom closer. It'll be a shorter bond. We can also see the bond length and bond strength. A triple bond is the shortest bond at 1.20 angstroms. And it is the highest bond energy. It takes the most to break. The reason for that is because there are 6 electrons holding those 2 atoms together. There's 1 sigma and there's 2 pi's. Altogether, that would be 3 bonds or 6 electrons. For the double bond, again, that's 4 electrons. We have 1 sigma and 1 pi holding those 2 carbons together. And just for the single bond, the longest bond, the weakest bond, the bond energy that's the smallest cost, easiest to break, releases the smallest amount of energy when formed. We just have 1 sigma bond and no pi's there.